All right, so uh, we're going to continue today with divide and conquer. It's going to be another fun math day. We're going to look at two math problems, solve one fully, and then the other one is for your programming assignment next week. In fact, this is it. So what I want to do is I want to do this very, very simple computation. I want to compute a raised to the n for a very large n. All right. Now we're talking about millions, billions, whatever. Right. Mod m. Okay. Just want to make sure that this works. Yeah, it's working. Good. All right. So, all right. Well, how would you go about doing this? Let's do this in code. All right. Let me go ahead and create a couple of values here. Let's go ahead and say that a is equal to 12. N is equal to, I'll keep it small. We'll pump that up after we get this to work. And then M will be 17. So my goal here, goal, is that too small? I can go up one, no, that's too much. Is compute A raised to the N mod M. So Pythoners, lots of Python experience here. Help me out. Oh, okay. A star star n mod. How do I do mod in Python? Same as any other language, m, right? And store that result there. What? So yeah, I don't know. Let's find out. I tested it right beforehand, and I was a little bit surprised. So let's go ahead and go with print formatted here. And I'm just going to format this as a raised to the power n mod m is equal to, and then the result here. There we go. And let's go into CSE 310 here. All right. So Python demo. I don't know, is that correct? How do I know it's correct or not? Oh, do I not? Yeah, exactly. I thought I had it open, but I guess I must have closed it accidentally. So 12 raised to the 26 mod 17 is indeed 9. All right. We're good. All right, let's keep going. Let me mash my keyboard here. Blah, blah, blah. There we go. Very large number. Now remember, Python has Python 3 has native support for multi-precision integers, arbitrarily large integers. So let's go ahead and run this. And while we're waiting for that, I'm going to take that number and bring it over here to Wolfram Alpha and see what Wolfram Alpha says about that. Oh, 16. Okay. I was fairly quick. Fairly quick here. How long should I wait for this? Several billion years, probably. Right? So what's the problem here? This is not going to work. Let me show you another way of doing this. Basically what Python is probably doing under the hood. Yeah?
So when Python stores like that kind of large number, does it take a lot of bits, or do they compile it?
I'm sure that there's some, maybe it's using GMP under the hood. I mean, at the end of the day, what is Python written in? What is the interpreter written in? C. So it's probably using GMP as my guess. Or maybe there's something under the hood in NumPy. Although, no, it wouldn't be using NumPy in this case. I was surprised that NetworkX used, what is it, OpenBLAS? All right, and then why? That's usually used by NumPy, or NumPy or whatever. Right? But anyway, let's go ahead and just do this the naive way. Right? What would you do? Let me go ahead and kick it down to 26 again. I would say a to the 26 is equal to what? A times A times A times A. How many times? 26 times. Well, it's simple enough. Let's write a loop to do that. For loop, while loop, what? For loop, okay. For I in range of n, I will go ahead and say that A is equal to A times, or result is equal to result times A. So I'm multiplying by A one more time. And mathematically, it's okay if you want to mod this out as you go along to always keep it small. Those parentheses, strictly speaking, are not necessary, but I'll go ahead and put them in there for clarity. Right? I'm going to do this n times 0 up to n minus 1, so I need to start my result where? At 1. So it's going to go 1 times a times a times a times a times a n times. Okay? Let's run that, and we get the exact same answer as before, 9. Right? Oops. There we go. All right. All right, let's kick it up again. What was that number? I want to make sure that I have repeatable tests here. So that mashed keyboard, I'll use the exact same number here. All right. While we're waiting for that, let's analyze this algorithm. All right. So really quick here, for I running from 0 up to n minus 1, r initialized to 1, right? R is equal to R times A mod M. That's it, right? There's our pseudocode. Let's go through our 5-step process here. 1, what's the input? Well, the input here is, remember, we're raised A to the N mod M. Which one of these, so we've actually got 3 inputs, right? Let's simplify it. Let's choose the most relevant one. This algorithm is controlled by N. I would say that N, that's why I named it N, right, is the input. Right? Remember the 5-step process though. The second one is just as important as the first, even, and sometimes it's not trivial like this one, like in this instance. What is the size? Think about it and we'll come back to that step. What is the size of an input of a number? What's the elementary operation? It could be multiplication. It could be the mod, which is a division remainder, right? Doesn't really matter. Let's just go ahead and say multiplication. All right. So 4, how many times is it executed with respect to the input size? Well, how many times do we execute this loop? N times, right? N times. So 5, naively, we would say that this is order N. It's linear, right? That's perfectly reasonable. Is it perfectly reasonable? It's been at least 2 minutes now. Let's find out why it's not perfectly reasonable. The answer lies in the second step that we skipped here. What is the input size of a number? Do we remember this? If I say 1, 2, 3, 4, right? Do I say that the n, if n is that, right? Do I say that the size is 1,234? Did it take me 1,234 symbols to write that down? No. How many symbols did it take me to write that down? 4. N is 1,783,243. How many symbols did it take me to write that down? 7. So the input size is growing with the magnitude of the number, but the input size is not the number itself. That's the input. This is the input size. In general, how many digits does it take to write down a number n? There's this nice mathematical thing that we have that tells us exactly that. Although, for whatever reason, in K through 12 education, they don't tell you the obvious thing about it. A logarithm. What is the purpose of a logarithm? Yeah, see, they never say what the purpose of a log. What is it? It's to give you, it's to quantify the magnitude of a number. It's to quantify the number of digits, base 10, are required to write down that number. Of course, you have to take the ceiling. Right? They always do it. Logarithms are always couched in the presentation of the natural logarithm. And maybe that's why it's confusing, because what is the natural logarithm? base e of n. Have you ever heard of a base system that's 2.71 symbols? No. I mean, it has other uses besides telling you how many digits something takes. So, but that's the obvious interpretation of a logarithm. Right? Now, we're base 10 because we're humans. But now let's think about a computer. Computer's not base 10. If I've got a number in binary, the number of bits to represent n is log base 2 of n. But as all self-respecting computer scientists, we never actually write, we never actually write the base because all bases are the same within a constant. And our base is always going to be 2 because we're self-respecting computer scientists. Right? So log 2, right? And of course, technically, you'd have to take the ceiling, but whatever. Right? Do we want to see why? I mean, usually this is the interpretation I give. That suppose that I gave you a certain number of bits. Say I gave you 1 bit. What is the maximum number that you can represent with just 1 bit? 1. Right? What if I gave you 2 bits? 3, which is 1, 1. Right? And this is also 1. Right? What if I gave you 3 bits? 1, 1, 1. And that's what? 7. Right? Dot, dot, dot. What if I gave you k bits? It'd be 1, 1, 1, 1, dot, 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 1, 1, k bits here. 2 to the power k minus 1 because you have to start at 0. Right? That was the question forward. The question originally is how many bits does it take to represent k? A number n. Right? 2 to the k minus 1. Now we're answering the question in the reverse order. What is k? Right? Suppose I have a number n. What's the minimum number of bits that I need to represent that number? And we've got n is equal to the 2 to the k minus 1. All right, so take minus 1 on the other side, right? Is equal to 2 to the k. And now how do I get rid of that 2? Log base 2. That gives me k. Ignore lower order terms here. Ignore the fact that you're in base 2. And you've got your answer right there. Right? That's the input size. Right? So all the way back over here, now we can answer this question. What's the size of n? It's not n, it is log n. Give that another name, big N. That's our actual input size. Yeah?
So the input size isn't how many times the program runs.
Nope. Nope. Not in this case, at least, because our input is a number, not a collection. Right?
If it's a collection.
If it's a collection, well, it depends on the algorithm, right? Again, it's all context. I could have an algorithm that takes a collection, but that's not what the running time is all about. It's about that thing over there that is also an input. So it's art rather than science, right? Which is math, right? So if we've got this relationship right here, my order n algorithm then becomes what? Solve for little n. Well, how do I get rid of a log? Base 2? I raise it to the power, right? And so order n, which we thought was linear because we didn't do the analysis correctly, is order 2 to the n, big N, where that's our actual input size. Is that linear? Absolutely not. That is exponential. Right? It will take centuries, billions and billions of years to do something like this. So, how did Wolfram Alpha do it? It didn't take billions of years. It did what we did at the very beginning of this divide and conquer strategy discussion, right? When you write down a bunch of numbers, 8, 4, 7, 2, 3, 1, 8, 9, right? You work it bottom up, right? You sum those two, you sum those two, you sum those two, you sum those two. But we're not talking about sums here. A to the n is about multiplications. Dot, 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 a to, right? But you can do the same trick. These two multiplications, let me add those, these two multiplications. Guess what each one of those is, though? They're all the same. Do I have to do this n divided by 2 times? Do I have to do this one and this one and this one? No, just do it once, right? Likewise, do I need to do, if I eventually got, a squared here, do I need to do a to the fourth, I just do it once, and then bring it all together. A to the 8th, dot, dot, dot. What am I doing here? Let's look at it from the bottom up. I want to compute, say, a to 77. Let's break that down. That's a to the 64th times a to the, what's left? Darn it, I don't want to have to do that math. There we go. A to the 13. All right. Well, we can break that 13 down further. A to the 8th times a to the 5th. Right? A to the 64, a to the 8th. All these are just multiplications here. A to the 4th, and then a to the 1st. Right? Tell me about each one of those exponents. It's a power of 2. How do I get those? Well, I can go ahead and get a squared with one multiplication. Right? All I have to do is square that again. A squared gives me a to the 4th. That's another multiplication. What if I square that again? A to the 8th, or a to the 4th squared is going to give me a to the 8th. That's 3. A to the 8th squared again gives me a to the 16th. That's 4. A to the 16th squared. A to the 32nd squared. That one gives me a to the 32nd. And then I just feed that into the next step. A to the 64th. 4, 5, 6 multiplications so far. Instead of the 77 that our naive Python program was going to make. 77 multiplications, which is a blink of an eye, it doesn't matter. But now I've got it down to 1, 2, 3, 4, 5, 6 multiplications. Plus, of course, I have to do all these multiplications. 6, 7, 8, and 9. Only 9 multiplications once I've got all of my squares, right? All of my powers of 2. So in total, only 9 multiplications versus 77. Okay? Let's codify this. In other words, let's write some pseudocode to do this. It's called repeated squaring or binary exponentiation. Why binary exponentiation? Because what are we doing? We're going 1, 2, 4, binary, right? Powers of 2. And then we're using them as exponents in our values. Right? So here's my input. Right? My input is going to be a, m, and n, but we're going to look at n being in binary. bk minus 1, bk minus 2, dot, 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 b1 and b0. All right? So thinking ahead here to next Friday when you have to have another program to do this, immediately, how do you get the binary representation of a number in Python? It's a bin function, right? And you're done, right? But otherwise, our output here is going to be a to the n mod m. Okay. Forgot to say that we are online. If you have any questions, you can post to Piazza or YouTube. But and people are watching. Great. But at least say hi or something. I don't know. Anyway, so I'm going to go ahead and come up with a term here. I'm going to start my term at a. You'll see why here in a second. Basically, let's come back to this example here. Now, there are some values here that I did not include, right? For example, what about a squared? What about a to the 16th, a to the 32nd, right? Why aren't those over here? They are, but they have a coefficient of 0, 0, 0, right? That's basically what you, sorry, not a coefficient there, but a coefficient up here, right? Why? Because that makes it 1, 1, and 1. So that when you go to multiply it, right, you actually do multiply it, it's just that you end up multiplying it by 1, right? Okay? I'm going to start my term here at A. And I'm going to check my lowest order bit. I'm going to start at the lowest order bits, and I'm going to work to the highest order bits. So if you were to convert this to binary, you have to start at the right and then work your way up, if it's big endian or whatever. Yeah?
So when I said input size, are we still doing it linearly?
Well, we'll analyze it once we've written it.
Okay.
Right.
But before we weren't doing it.
Nope. Before it was exponential. Did I let it keep running?
So we're doing
It's exponential.
but we're doing it as many times as the n is.
We're doing it that many times.
And that's not linear.
Oh, no. Because how many bits does it take to represent this thing?
Yeah.
Wolfram alpha, log base 2 of that. The actual input size is only 82, not that big mashed number. Right? It only takes 82 bits to, well, 83 bits to represent that. Yep. All right, so if the lowest order bit is 1, then we start out with a product of alpha, or A, sorry. Right? Else, our product will be 1. Now this is like me starting R at 1 and then R times A times A times A times A. If I started it at 0, it'll always be 0. But we're starting it out at either 0 or A because I'm looking at this lowest order bit here. If it's a 0, right, then we don't contribute it, right? Its exponent coefficient is 0, and so the entire thing becomes 1. Otherwise, its exponent is 1, and we want to make sure that we're counting it. And now what we do is we start squaring. We repeatedly square things. For I running from 1 up to k. Now remember, that starts here and works its way this way. The lowest order bits first. So if you convert it to a string, a binary string, you need to work backwards or you need to flip it and then work forwards. Right? So for I 1 through k, our term here will be squared. Term squared. And we can also mod that out by m so that it doesn't grow too big. Right, we can keep it small. And if that bit, b sub I, is equal to 1, then we contribute it to the product. Product will end up being product times term mod m. There we go. And that's it. I'm not going to implement it because that's your job next week. Right? Your job next week will be to do that. You cannot use built-in functions. There is another built-in function that will do this efficiently. I'm not going to show it to you. You can use it to verify your answers, but obviously what can't you use, no matter what? That guy right there. Yeah.
So we have to turn it into binary first.
Binary, or you can use some bit twiddling tricks if you want to check those out.
Is that internally?
Well, bit twiddling tricks like this. I'm going to kill this. This is all bad. Something like, what I mean by bit twiddling is something like this. If I've got, say, A is equal to 7, what is that in binary? 1, 1, 1, right? If I'm going to, I don't know, if I'm going to check the lowest order bit there, what do I need to, I can say that bit lowest bit is equal to A, mask it with 1, right? And then print lowest bit. 1. Why did I only use 1 ampersand? That's the bitwise or and operation, right? So think about these in binary. A is 7, 1, 1, 1. What is 1 in binary? 0, 0, 1, right? And so when I AND them together, what do I get? I get 0, 0, 1, right? The lowest order bit is 1. Now what if it were 6? What is 6 in binary? That. And now when I mask it, I get 0, right? So I'm going to get 0 or 1 out of that computation. Now, obviously, then I want to look at the next bit, and the next bit, and the next bit. To do that, what you can do are shift tricks, right? This is all bit twiddling, right? Because you're twiddling with the bits, right? Sounds very English, right? I'll shift it over by 1, right? A is equal to this. Now let's print A. Now that's a right shift by 1 bit. So again, if I've got A is 1, 1, 1, and I shift it to the right, losing that lowest order bit, what do I get? 0, 1, 1, which is what? 3? 3. I can go the other way. What do I end up getting here? 1, 1, 1, 0, which is what? $14? There we go. Can't do algebra in my head, but I can do binary in my head. Not very big, but whatever. All right? So you can use bit twiddling tricks like that if you want to. Right? Okay. Now, analysis. Let's go back over here. So, what is, the same as before, our input is going to be n. Our input size is going to be log n. Now, in terms of everything that I've written up here as part of the input, how many is that? K. All right, K bits. Okay. So, what's the, no, I guess I didn't finish this. There we go, there and there. Right? What is our elementary operation? You could be this comparison here, or the square, or the mod, or whatever. It doesn't matter. It's one thing. How many times does this execute with the, 3, your choice? 4. How many times are we executing this for loop here? K times. Not n times, K times. And that's equal to log n, because we did the proper step 2 in this case. 5, this is going to be order log n, where log n is the input size, and if we substitute in a better variable for that, it's going to be linear. Right. It's not logarithmic like binary search. It is linear with respect to the number of bits in the input. Yeah?
What does term and product stand for?
Term is our term, so a squared, a to the 4th, right? Term is updated to each one of these things. Right? The product is the output, final output here, product. Right?
To calculate the product of the...
Right, because, look at what we're doing. We're going a squared, a to the 4th, a to the 8th, a to the 16th, a to the 32nd, a to the 64th. Remember that we wanted to compute a to the 77.
And we multiply it.
Yeah, exactly. So let's write this out. What is 77 in binary? I can't do that one in my head. 77 to binary. All right, 1001.
So you have 1 and 3.
I'll write it down here. 1001 101. There we go. All right. And so what are you doing along the way here? right? You're looking at first the lowest order bit, 1. So what is my product going to end up being? This is my term as I'm going along here. It ends up being, that's the initialization, right? That's these lines right here, right? Now I compute the term by just simply squaring, but each one of these I look at the bit, right? The bit is 0 here. So do I do anything? 0, nothing. And it remains A. The next one is 1. And so I say A times the term, which is A to the 4th. The next one is 1. So what do? A to the 4th, 1, and then A to the 8th. Right? Nothing, nothing. So nothing, nothing, and finally 1. So this gives me A to the 1st, I'll keep that, A to the 4th, A to the 8th, A to the 64th, which is equal to A to the 77.
The multiplication is a hard thing.
Yeah, mod is that you're just taking a remainder there.
So mod isn't, even though it's just a large number.
Not really, because I mean it's integer division. So, and you're as long as you're keeping it small throughout this entire process, it's going to be proportional to m there. It's just one thing. Again, you could say that that's your elementary operation. That's the most expensive thing. Well, fine. You just do it once still, right? Twice if you count that, but that's the worst case scenario, right? But then you're also doing another multiplication here. So 1, 2, 3, doesn't matter. What really matters is its order. Okay? So again, I'm not going to do that. I've given you more than enough to help to get that started. But that's, yeah, I'll go ahead and cut and paste all this that I was talking about the entire time, but I wasn't actually writing down. Say again. Probably, yeah. Don't do that though. You can't do that. You can check, yes. Speaking of checking, we're not going to get to it today because that took too long. But one thing with the next exercise here, I do want to introduce you to formal unit testing in Python, just because I bothered to learn it last year, so you should bother to learn it too, and I'll teach it to you. Right? But to start that out, we need another math problem. Very, very similar, by the way. And by the way, most of these math problems that I'm doing are building us up to an RSA crypto system, which is not next week, but the week after that. Right? All right, so the greatest common divisor, or GCD. The definition is that A divides B, and we write A divides B. Yep, that's rendering correctly. If there exists an integer k such that we can write B is equal to A k. More generally, any integer can be rewritten as B is equal to A k plus R. In fact, I'm going to change that. AQ plus R. Right? This is just basic integer division. I mean, if you go back to grade school, before you were introduced to the fact that you can divide numbers in half and you have 0.5, that's how you did integer division, right? B and A are, one of them is the divisor, one of them is the dividend, right? What is Q? Q stands for something. The number of times that the divisor goes into the dividend. Quotient, right? And R is also chosen for something. R is the remainder, right? All right, so we've got our terms down here. You can also have congruences, right? You can do something like this. An equivalent notation is a congruent, that we can say that A is congruent to R mod M, and we would write that A is congruent to R mod M. Now you might have heard the word congruent in other contexts, like two triangles are congruent, right? If they're if they have some similarity, right? These numbers have similarity and they're congruent, right? Equivalently, you can say that m divides a minus r, or that a is congruent to the remainder of mod m, if and only if you can write it as a is equal to mk plus r, right? And I will keep k in that case, all right? Now you can talk about two numbers and its divisors, right? The greatest common divisor, or GCD, right, of two integers, a and b, written as GCD, I don't know, does this do it? GCD of a, b, how does that render? Okay, yeah, it's part of LaTeX, right? Is the largest integer that divides both a and b. Right? So for example, what is the GCD of, say, 60 and 210? Well, does 60 go into 210? Not evenly. Generally, how would you do this? You could do this by breaking it down into its divisors, right? 60 is equal to what? 2, and then 30 can be broken down into 3 and 10, so 5 and square up here. Okay. 210, that's 2, so that's 105, that's 5, 105, that's 35, right? And 35 is going to be 7 and 5 squared. All right, there we go. So how can I formulate the GCD? I look at each one of these and say, okay, well, 2 divides both of them, but 2 squared doesn't divide both of them. So I only take one of those 2's. 3 divides the first, but not the second. Right? Is that right? That's a,
Wait, no, there's a 3.
yeah, what happened to my 3?
30 times 7.
Damn it. Is that correct? 6, 42, 25. That doesn't seem right. Damn it. Factor 210.
Yeah, there's only one 5.
2, 3, 5, 7. Thank you. 2, 3, 5.
There's only one 5.
Yeah, 1, 5. There we go. All right. So times 3, but there's only 1 5, and then this one does not have a 7, so I'm done. So what's the GCD here? 30. 30 divides 60. 30 divides 210. All right? But to do it this way, what did I have to do? I had to break down and factorize it. Right? I had to find all of the factors. That's an extremely difficult problem, and hopefully it will remain forever an extremely difficult problem. Right? Not that it's straightforward. Right? You can use the sieve of Eratosthenes, right? By just dividing by each prime factor. Does 2 divide it? Yeah, how many times? Okay, well, it divides it 2, so we got that. Now, that's a smaller number. Does 3 divide it? Does 5 divide it? Does 7 divide it? Does 11 divide it? 13, ... Right? That's brute force, though. That brute force will be exponential. We need a better way to compute the GCD. To do that, I'm going to give you a larger example here. Right? Yeah, here we go. Right. So let's write out the fact that we've got A and we've got B here. 1768 and 184. Now remember that basic algebra says that you can rewrite any integer, right? Any integer can be rewritten as this. Right? If we just take A and B, take B divided by A, we would get a quotient and we would get a remainder. So let's do that. 1768 is equal to 184. 184 goes into 1768 how many times?
9.
Oh, good.
Really?
Yep. that was easy. Why? Because you can go, all right, 10, that's 184, 1840, that's too big, but it's not big enough. We can go down 1 and be done. And the remainder is? Anyone? I can't do that off the top of my head either. 112. Now, the GCD of these two numbers has to divide them both, right? So the GCD, if it divides this thing, it has to divide the entire right-hand side. And since it divides this thing right here, it doesn't have to divide the quotient, right? But it does have to divide the remainder. In other words, the GCD, big C, GCD of 1768 and 184 is equal to the GCD of 184 and 112. What did I do? I divided the problem down into a smaller problem. Right? I've got a big number and another big number, let's say. Right? I had to retain one of those numbers, but that big number is now a smaller number. Well, guess what? I can continue. 184 is equal to 112 times some quotient plus a remainder. 112 goes in how many times? Just once. With a remainder of, that should be easy, 72. Right? So now the question is, can I do the GCD of 112 and 72? Right? Dot, dot, dot. When do I stop? Well, when there's no remainder, right? When there's no remainder, what would I end up with? GCD something x and the remainder of 0. Right? That means stop. You found the GCD right there. Right? So if you want to take this particular example, you'll eventually stop at GCD of 32 and 8. Which is equal to, well, 8 goes into 32 evenly with a remainder of 0. So our GCD ends up being 8. That's Euclid's algorithm. It's over 3,000 years old, right? And it is just as efficient today as it was 3,000 years ago. But we can more easily program it. Yeah, let's go ahead and create a really quick implementation here, because we're going to do a better implementation next week. I'll call it GCD, right? It takes A and B. Right? It's extremely simple. All we need to do is, while B is not equal to 0, right? That's going to end up being our remainder. Right? I'm going to be very, very Spartan, very, very conservative on all the variables that I create here. I'm just going to create a temporary variable to hold B. I'm going to say that B is equal to A mod T, mod B, A mod B. I'm taking A divided by B, right? And then I'm going to update A to be T. That's all I'm doing, right? I'm taking A divided by B, and then I'm shifting that over. Divide it by whatever the remainder is. This is giving me the remainder right here, right? This is the, remainder, right? And then I shift things over. A divided by B, give me the remainder. Shift that B into A, shift the remainder into B. Over and over and over again. Let's try it out. G of GCD of, what was our numbers again? 1768 and 184. Print, and let's format that. GCD of A and B. I guess I should have done A is equal to 1768 and B is equal to 184. We're good on time. A, B is equal to G. Good? Oh, sorry, what? No, oh, thank you. Good. Did anybody dive deep into that MyPy to see if it will catch things like a lack of a return statement? Okay. At this point, I think that you can return, what is it? B? Or A. There we go. All right. There, that should be okay. Python Euclid. Oh. There. Formatting issue. 8. Excellent. Mash the keyboard. Mash the keyboard. All right. Take that, move it over to Wolfram Alpha. Oops. GCD of this, and what's the second number? Mashed keyboard. 1. What does that mean? They're not necessarily prime. They could be prime. They're co-prime, relatively prime. Let's find out what Euclid does. That's 1. All right. Fine. If I add a 2 here, I'm assured that it's at least not co-prime anymore. Why? Because they're both even. Mashing the keyboard doesn't help at all. But at least I get some confidence here that these things are big, right? I know how I could make this do this further. What I could do is could say multiplied by 210 and multiply that by 210. Right? And we know that the GCD before of 210 was 30. And so times 2, because I did that before, is, now it's 420. Oh, cool. Oh, 210, yeah. Okay. Yeah, 210 times 2. Thank you. 420, that was not intentional at all. Times 210 times 210. 420. All right. Cool. How can we be more formal about that? So we'll take a little bit of a digression on Monday and talk about unit testing in Python. It is this nice built-in thing. Actually, you might need to actually use, I think it works without, that it comes with just regular old Python. If not, you might have to pip install it, unit test. And the magic of it, if you prepend any function with the word test underscore, that becomes your unit test. That's it. That's the convention. I mean, it's kind of like it's kind of like JUnit, right? You, instead of naming it a specific thing, you decorate it with an dang it! Now I'm drawing a blank here. The @ symbols are annotations. There we go. You decorate it with an annotation. In Java for JUnit. This is you name the function certain things and it discovers them automatically. Right. So we'll look at that on Monday then.